Next marathon session on sources of magnetic field and Ampere's law. So in our previous lecture, in our previous marathon, we have seen how magnetic field affects moving charges as well as current carrying wires and what are its effects on current carrying loops. Today we are going to focus on how magnetic field is generated by different current carrying conductors and in different geometries, and we are going to see some important properties, theorems, etc. With me, Shreyas, your master teacher for physics, going live, and also your anchor for this channel, We Enthuse guys. Welcome Sanspriya, VK, Vimla, Jumna, Kirito, Nilesh, welcome Selva, welcome Dakshesh. Hello everyone, hello, I'm very good. Excellent day, hello Aishwarya, hello everyone. So guys, I teach physics not only on YouTube but also in the regular batches at Vedantu. Because a lot of people had that question, sir, do you only teach in YouTube? No, I do teach in the regular courses as well as the micro courses. What are these micro courses? You will understand when I tell you about it after some time, but you can definitely enroll yourself, and if you are already enrolled, then you can definitely find my micro courses as well. And if you still want to get in touch with me, you can get in touch with me on my Instagram handle, Shreyas_Vedantu. Guys, I have been coaching, I have been training students for a long time for JEE, for mains, advanced, BITSAT, and I know that if you prepare for JEE, you automatically get prepared for boards, BITSAT, CET, you name it, all the competitive exams out there. So focus on the portion, don't worry about the examination. Automatically, once this portion is completed in our flash series, and we are going to do it in the next couple of weeks, let me tell you that yes, physics at least I'm going to complete it by end of Jan or February first week or so. And during this time there are going to be lots of sessions on Menti, KVPY, etc. So stay tuned guys. Hello Fida, hello Khushbu, hello Satish, hello, welcome everyone. I'm very good. So guys, this channel is very unique because this is an English medium channel, and I don't think there are many English medium channels at least which are popular on YouTube. So guys, for all the people who wanted to learn in English, this is the channel to be. So guys, if you have found this channel, you know what to do. Go hit the subscribe button down there, because only when you subscribe you will get all the important notifications, news, lectures, Menti quiz updates, all these things. Go hit the subscribe button guys right away. It's for free obviously, and there is one more thing which you can do for free, and that's the like button guys. Go press that like button if you have not done it yet. Show me all the support, show me all the love by hitting that like button if you have not done it yet. So welcome guys, welcome. So let me tell you the schedule. So this was the schedule for this week. We are on the last day of this week. So in case you have missed any of these important sessions, I would heavily advise, like, please go and watch all these lectures, very important. So there was a marathon on Thursday, there was a KVPY session on Tuesday and Friday, there was a special session for 11th standard on Monday, and on Wednesday we had errors and measurement related discussion. So today we're going to complete magnetism field, sources of magnetic field and Ampere's law. And if you have missed any of these Menti sessions, go ahead, check out the replay. And chemistry Menti quiz will be on Sunday, 9 o'clock in the night. So do not forget that. All right, so let's begin. I hope you guys are ready now. Hello Sneha. Hello, welcome everyone. Hello Shreya. Hello Demi. Hello Khushbu. Hello Kirito. Welcome. Yes, so today's marathon is going to be again of 2 hours. Welcome everyone. So guys, I hope you have again come prepared with all the juices and all the biscuits and the sandwiches, whatever you want to, momos, whatever you want. So you can tell me in the chat box what have you come prepared with. I will tell you what I have prepared myself with. In a bit you will be seeing me eat whatever it is. Any guesses what I have come prepared with for my energy, for my for eating something? Hello Aviram, nice to see you over here. Okay, so Complan, no, it's not Complan. Yes, it's going to be almost 2 hour session. So guys, be prepared. All right, juices, yes, it is there. But no, today it's not Little Hearts. It's not a sandwich. Okay, you'll find out, guys. So stay tuned what I'm going to eat today. All right, chalo, let's get going. So first, let's talk about Oersted's experiment, which was it's very famous, guys. I mean, come on, you would have studied this in 9th or 10th grade, obviously. That he found out that when you pass current through a wire, then if you have a magnetic needle around it, it deflects. Yes. And if you reverse the direction of current, then the deflection also reverses. And if you pass more current, then the deflection increases. And if there is no current, then the deflection is not there in the magnetic needle. This is what Oersted discovered, and he then realized that yes, current carrying wires produce magnetic field. Understand? So moving charges, so whenever charges move, they produce magnetic field. Remember that. And it's very easily seen over here that, see guys, when the switch is open, the needle does not deflect at all. Okay, so when the switch is open, no current, no magnetic field. When the switch is closed, the deflection is on one side. But when you reverse the polarity, look at that, when you reverse the polarity, the deflection is on the other side. So the direction of the magnetic field depends on the direction of current, number one. Number two, the strength of the magnetic field also depends on the strength of the current through it. Okay, and number three, understand the strength of the magnetic field also depends on how far you are from the current. All right, so that's how it is. All right, so lots of food related discussion going on in the chat box. Very good, keep it up. All right, so now let's see very important things, guys. The magnetic field due to different geometries. Focus on the session as well, guys. I know you guys are feeling a little bit hungry because we started the discussion on food, but focus on the session as well. So what is the magnetic field due to different geometries? First, only the direction, not the magnitude. So let's just focus only on the direction, and some very conceptual questions coming on this. So keep paying close attention to the diagrams, very important. First thing, if you have a wire which carries current, then the magnetic field around it is in the form of concentric circles. Okay, the magnetic field is in the form of concentric circles. But whether the magnetic field is this way or whether it is the other way, that is given by the right hand rule, guys. So remember the right hand rule. So let's say if the current is going up, use your right hand. Come on, use your right hand, hands up in the air, and show some dance moves. All right, so hold the wire, guys, and let the curled fingers go around it. So the direction of the curled fingers show you the direction of the magnetic field. So understand, if you're on this side, the magnetic field is going to come towards you, and if you're on the other side, then the magnetic field is going to go inside. That's why there is a cross over there. So use your right hand, and that's it. So if this current reverses, then you'll have to curl your fingers the other way around. So if you're on this side of the wire, the field is going to come towards you, and if you're going to be here, then the field is going to be away from you. Is that clear? Let me know. Dhanush, you will complete 100% syllabus with me, so stay tuned. Don't worry, 85% is not enough. We have time, we are going to do 100%. All right. Very good, excellent, guys. Nice to see all your love, support, and your chats. Very good, keep it up and stay tuned. All right, so this is the magnetic field's direction due to a straight wire. Next, so before that, let me show you the school simulation, or you can see the graphic out here, how the current is going in one direction, and you can see how the magnetic field is in the circular direction. And just hold the thumb down, you can see how the magnetic field curls around that wire. So this magnetic field is there everywhere, but the farther you go, the intensity, the strength of the field decreases. So remember this. All right, so having said that, let's go ahead to the next geometry, and that is nothing but a coil. So we are done with a straight wire. Now a coil, guys. So if there is a current flowing in this way, then the magnetic fields are going to be this way for a loop carrying current. Now whether it's going to be this way or whether it is going to be this way is again given by the right hand rule. Come on, use your right hand, guys. Yes, use your right hand, but this time the current direction will be given by the four fingers. Yes, the direction of current is by the four fingers out here. This thumb will give you the direction of the field. Look at that. The direction of the current is given by the four fingers, and thumb gives you the direction of the field. Yes. So guys, don't get confused. Sir, when is this thumb going to give you current? When is this thumb going to give you field? Guys, whichever is curling, use that as your fingers, four fingers to curl, and the other thing will give you the other physical quantity. In this case, I'm going to use this for current, so naturally thumb will give you direction of field. Similarly, in the previous example, the field was given by these 4 fingers, the current was given by the thumb. So depends guys, from geometry to geometry, so don't sit and by heart it, it's very natural, you can go ahead with it. All right, so the 4 fingers is the current, this is the direction of the field. You can see as you go away, the field lines disperse out and the field intensity weakens. Okay, so as you move away from the coil, so look at this again over here, if you curl your fingers this way, the current is going like this, the magnetic field is in this direction. As you move away, the field reduces. Here the field is very strong, again the field will become weak as you go towards the left side. I hope this is clear. Very, very important. Yes. All right, Vimla, no, this is a 12th standard topic. This is not 11th standard topic. All right. So, all right, all right. Yes, if you have a book, make notes. Very good, Ankit. Keep it up, keep it up. Yes, make notes, make diagram. Very good, Khushbu. Very good, VK channel. All right. So now, next is solenoid. Now, I'll tell you what is a solenoid, guys. Imagine you have a loop over here, another loop, another loop, another loop, many loops like this. So if you have many loops together, okay, one after the other, not in the same plane, one after the other in different planes, so it will look like this. One loop here, one loop here, one loop here, closely packed. So that is nothing but a solenoid. Now if you look at it carefully, guys, think about it. These magnetic field lines, because of a single loop, look like this. Now you stretch this diagram, doesn't the diagram look exactly like this? Or visualize it the other way, compress this diagram and make it into a single coil. You will see that the field lines look exactly like this one, I hope you can see that. So solenoid is nothing but just like a stretched wire in different planes along the axis. That's it. So this is a solenoid. So there is a coil which is wrapped around something. So that is nothing but a solenoid, and current which flows through it produces magnetic field. Again, look at that. The current is going like this and going back, like this and coming back. So it's going like this. So if you curl your fingers this way, your thumb will point in the direction of magnetic field. You can see that. So the current goes like this. The thumb points in the direction of magnetic field. Very important. Very good. Very good. Yes, 1D, 1F, WWF, 3F2. Is that a name or a password of your email address? All right. So yes, this is enough. So this is how the magnetic field looks like due to the current flowing inside a solenoid. Look at that, guys. Look at the direction of current. Use your right hand and see whether right hand rule is working out here. Curl your fingers in the current direction. You will see the thumb points in this green arrow mark, which is the magnetic field. Very good. All righty, all righty. Very good. Very good, Pincy. Very good. All right. Now, so the next thing is toroid. Now, don't get scared by toroid, guys. I'll tell you what. See, guys, if you take a loop and stretch it, it becomes a solenoid, correct? It's nothing but many loops. Now, this solenoid, you turn it around. Yes, you make this end fall on the other end by, turning it like a loop. All right, like a loop around here. So imagine if you take a solenoid, bend it and close the ends. So these field lines will not be able to escape. Where are the field lines escaping? At the end, right? Imagine if I place this end, wrap it like this and put it over here, the field lines won't be able to escape. So the field lines will be just passing inside the solenoid, that curved solenoid. That curved solenoid is nothing but called as a toroid. So it's nothing but many loops over here. So there is no space to come out. So what are these dots and crosses? This cross represents the current is going inside, going from behind and coming from here. Again going from the top, again going from behind and coming up like this. So the currents are going like this. The currents are going like this. So again, if you take your right hand, curl it this way, the thumb points in the direction of magnetic field. So all the magnetic fields are trapped inside the toroid. There is no field outside the toroid. Is this understood? There is no field outside the toroid because the field lines are now constrained to move inside this toroid. There is no escape out there. Very good. I hope this is clear. All right. Okay. Okay. All right. Everyone understood? Okay. Very good. Very good. Fida, Jumna, VK, Kirito, Princey, Shreya, excellent. Science Priya, excellent. Danny. All right. All right. So let's start doing some questions. By the way, again, the simulation for toroid, guys. Look at that. How the current is moving. Looks like some virus to me anyways, or some crazy bacterial structure, but anyway, so this is nothing but how the current is moving. And if you curl your fingers, guys, you will see the thumb points in that green arrow mark direction. Just curl your fingers, visualize it, it will point it that way. Yes, toroid is very cool, I agree. All right, very good reply. Princey, yes. Mohammad, Pakka, very good. Excellent. COVID toroid, yeah, very bad. All right, so here's a question coming up on your screen right away. Let's solve this. I'm going to solve a lot of questions today, guys, so that your concepts are very clear. So the question out here is, there are two current carrying conductors as shown in the figure. What is the direction of field at this point, only the direction, which is equidistant from both the conductors, assuming this current I1 is less than that current I2. Okay, so let's use our right hand rule, guys. Come on, let's use our right hand rule. Put your thumb in the direction of current. Automatically your fingers will curl like this. So you can see on this side, oops, 1 second. On this side, you will see the magnetic field is going inside. The magnetic field is going inside. I'll call it as B1 because you can see the fingers are going inside. Now because of this wire, if you point the thumb in this direction and if you curl your fingers, you will see by the time the fingers come from this side, they are coming towards you. Just curl the fingers, you will see on this side it is coming towards you. So hence B2 is towards you. Now which one is more, B1 or B2? Obviously the one which has more current will have more field. So this is more and this is less. So where would be the net field? The net field will be higher field, B2 minus B1, and it will be coming towards you. I hope this is understood. Yes, out, very good. A lot of you said, I don't know, different answers, but yes guys, it's going to come outwards. Very good. I think you are referring to the previous ones, by the way. All right, very good, very good, very good. Yes, Ankit, definitely you can make notes. This will be helpful for you. Very good, very good. Okay, next question coming up on your screen is this one. So let's try and do this. Come on, these are rapid fire questions, guys. Let's try and do this. You can post the answers if you want to solve it before me, but I'll be explaining the questions for all the people who want to understand it probably for the first time or seeing all these kind of questions for the first time. So now I want to find the magnetic field's direction over here, which is somewhere in the first quadrant, because of two perpendicular wires. Let's do this. Okay, so the current is going up like this. Put your thumb this way, fingers curl like this. So over there you can see the magnetic field is inside because of current in 1. All right, now because of current in 2, again put your thumb in that direction, right side, guys. Hold it towards your right side. Your fingers will curl like this. When you come from the top, the fingers are coming towards you, so it is going to come towards you. So that is B2. Now who is more? Oh, I2 is more than I1, so B2 is more and B1 is less. So the net field will be higher number minus smaller number. So it is going to be towards you again. I hope you guys got it. Very good, very good, very good. Very good, very good. Excellent, Saurav. Very good. Come on, join in. Excellent, Ria. A lot of people have joined in. Excellent. So now you are going to see, guys, by the end of today's class, you will become confident on sources of magnetic field, solenoid, toroid, Ampere's law, everything. You're going to nail it. I'm going to slowly scale up the levels of the problems beautifully. You will not even understand. All right. Chalo. You will slowly get used to the difficulty. All right. Let's scale it up. What is the direction of magnetic field at the origin? Was the direction of magnetic field at the origin because of this wire. Now there are two components in this. One because of the semicircle, second because of this wire over here. Now because of the semicircle, it's simple because the current is going this way. So curl your fingers in the direction of current. Curl your fingers in the direction of current. Where does your thumb go? It goes inside. So because of the semicircle, it should be inside. But then you might be like, sir, what about this straight wire? Guys, this point O is on that line, on that wire. So when you're on that wire, the field is 0. So the contribution of this wire, the contribution of that wire is going to be 0. So the only contribution is because of the semicircle, and that is inside. Hence the net magnetic field at the origin is going to be inside. I hope this is clear. Okay, so the contribution is 0. Very, very important when you are on that line. So understand, even here the contribution will be 0. Anywhere on that line, the contributions are going to be 0. Very important. Alrighty, let's go into the next question. Very interesting question. Let's see how many of you can actually get this. So slowly you are seeing that the difficulty of the problems is going to scale up. The current is going here, gets divided and meets here. What is the direction of the magnetic field at that point? What is the direction of the magnetic field at that point? Let's see, guys. First of all, this current, assume is I, it will get divided not equally. You're like, sir, why won't it get divided equally? Shouldn't the current get divided equally? No, the problem is this wire has some resistance, this wire has some resistance. Yes, and the resistances are not equal. If this resistance is R, this resistance is thrice of R. Why? Because this is 1/4, this is 3/4. Resistance is proportional to the length of the wire, guys. Remember current, electricity? Now I think you get it, that the current won't get divided equally. How will it get divided? In the inverse ratio. In the inverse ratio. Yes, here the current will be 3 times and here the current will be 1 time. So 1:3. So how do I divide I? How do I divide I in the ratio of 1:3, guys? Very simple. Divide I into 4 parts. So one will be I by 4 and the other will be 3I by 4. So 1 plus 3 is 4. So out of 4 parts you take 1 part, and out of 4 parts you take 3 parts. So 1:4. So hence the current over here, this is less resistance, so more current. More current. How much? 3I by 4. And here more resistance, so less current. How much? I by 4. Correct, guys? I hope you guys are understanding this. Now comes the tricky part. Now comes the tricky part. Observe this. Because of this side, the current is going like this. The current is going like this. So magnetic field should be inside, guys. Magnetic field should be inside. So because of this part, this 3I by 4, all right, the magnetic field should be inside at the origin. Very, very clear. Next, think about it. Because of this current, because of this I by 4 current, what will happen? The current should come outside. The current should come outside. Now here is the thing. Here is the thing. You might think, oh, will it cancel? Will it not cancel? Because some of you might be thinking, sir, 3I by 4 is more current. So 3I by 4 is more magnetic field. No. Think about it again, guys. Think about it again. You will easily understand that you can divide these into 3 parts. I by 4, I by 4 and I by 4. Each one of them will give the same magnetic field in this direction. Think about it. I by 4 in this part will give magnetic field towards you. I by 4 in this part will give magnetic field towards you. And I by 4 in this part will also give magnetic field towards you. And that effect will be same as only 1/4 in this side, which is having a current of 3I by 4. Don't you see, these 3I by 4s will balance just one 3I by 4? I'll repeat, won't these 3I by 4s balance this one 3I by 4's magnetic field? So hence the magnetic field, guys, the answer for this B net will be 0. That's the answer. What a brilliant question. Did you love this question? Lot of people get confused and give wrong answers. Lot of people give wrong answers. What an epic question. Yes, correct. Very good, very good, very good. Chamka, some of you are enlightened. Very good. Keep it up. So we are going to do a lot of questions like this. Stay tuned. Now remember guys, I was telling you about micro courses just some time back. Okay. So basically, what are these micro courses and what are these long-term batches, and what is Vedantu basically? Online teaching. A lot of people I know, including my relatives, feel that I conduct classes on Zoom or Google Meet. But guys, no, I don't conduct classes on Zoom or Google Meet. We have a special software called as Wave, and on Wave, there are so many features like quizzes, hotspot, yes/no questions, polls, and also there are 2 teachers simultaneously teaching you. You're like, what the hell? 2 teachers? How can they teach simultaneously? Well, I'll tell you what. So there is a master teacher like me who is teaching or conducting the class, solving all the problems for you, etc., conducting the polls, quizzes, etc. And there is a second teacher who is just for doubts, with whom you can chat. During the class, let's say you have a doubt. Obviously, the same teacher can't handle so many kids. So you get divided into small groups. And for each group, there is a class teacher. And you can ask your doubt to the class teacher, and the class teacher responds to those few number of kids. So it's a 2-teacher model that we follow. And at the end of the class, you have leaderboards, all the fancy stuff, so that you stay motivated and have a healthy competition with all your friends. And also, after every class, you get assignments, yes, so that you can revise all the concepts. And you have tests after every 3 to 4 weeks to challenge yourself, compete with others. And you get the booklet. Yes, the booklet has a lot of formulas, important derivations, important formulas and definitions and all that. And also lots of problems, level 1, level 2, level 3, so that you can practice a lot. So all of this along with micro courses. So what are micro courses? Micro courses help you excel in those topics where you're weak at or you want to study. For example, you want somebody to discuss H.C. Verma booklet. So I am conducting a special class only for H.C. Verma discussion, all the problems of H.C. Verma. Then somebody wants, sir, for KVP I want a class. Yes, there is a micro course for that. So somebody wants, sir, for boards I want tuition. Everything is there inside it, guys, and you have lots of amazing teachers. So you don't have to run around multiple coaching institutes. Everything is there at one place. So if you just take 6 months, subscription, the price for that is, the price for that is 39,000 for 6 months, half a year. But the discounted price after 50% discount is only 27,000, which is just 150 rupees per day. It's hardly anything. So guys, I highly recommend you this subscription for all the students who are preparing for 2021. And even there are subscriptions for, droppers for 11th standard. The prices, every detail is there in the link below. You can check it out after the video is over, or open it up on a separate tab and keep it aside. And do not forget to use the coupon code, because only when you use the coupon code you will get 50% off. Remember that. Alright, so use this coupon code and check it out. Really cool stuff. I know a lot of you are already in the pro subscription, and just because you love me, you still come over here. Very good, keep it up. Alright, so let's go ahead with the next topic, and that is basically Biot-Savart's law. So before this, what did we see? We just saw the direction. Now let's talk about the magnitude, guys. So get ready for the magnitude. So this is called as the Biot-Savart's law. Now, according to him, what happens is, if there is a current carrying wire, each small part of that wire produces magnetic field around it. So say for example, you take a point here, an element of length dl produces magnetic field dB over there. Similarly, another element over here will produce magnetic field over here. So the magnetic field at this point is the total vector sum of the magnetic fields due to every element on that wire. Is that clear? So this formula just gives me what is the magnetic field due to an element. If you know that, then by adding up all those magnetic fields due to all those elements, you can find the total magnetic field. Yes, so it's called as Biot-Savart's law. The T is like silent types. All right. Okay, so let's see. Okay. Now. Okay. Now, what is the value of this magnetic field? So first let's define. this is nothing but the element carrying current I. Okay, oops, element carrying current I. Next, dB. What is this dB? dB is the magnetic field due to dl element, only because of the dl element. Next, what is R? This R is nothing but the position vector. Remember, this is not the distance or the radius. A lot of people think this is radius. No, it's not radius, it's position vector. The symbol for position vector is R. Remember that. Position vector of that point with respect to the element. Understand? Because I am saying position of that point with respect to the element, the direction of R is here. If I had said position of the element with respect to the point, then the direction of R will be here. So position of this point with respect to the element, so the R's direction is this way. What is this R hat? This is nothing but unit vector. Okay, so R hat will be R vector divided by R. So that is unit vector in the direction of this R. That's it. So these things should be very clear in your head. Only then you can get full marks in boards and CETs, BITSAT and other basic first level questions in JEE Mains and other competitive exams. So this should be very clear what each term is. So the formula is dB vector is mu naught by 4 pi. That's a constant, and here you have IDL cross R a hat divided by R square. So that is the formula which you are supposed to remember. Okay, so this is something we have to remember. This is R hat. Remember, if you don't like R hat, you can substitute this R vector, then it will become R cube over here. But this is something you should remember. What is mu naught? What is mu naught? Mu naught is nothing but permeability of free space or vacuum. Permeability of free space. We'll be talking about this in a special lecture, don't worry about it. But remember, for now, the value of mu naught by 4 pi is nothing but 10 to the power minus 7 SI units. Very, very important. I hope you have noted down all these important pointers out here for Biot-Savart's law. Very good. Yes, to find net field, the net field, you have to just integrate dB vector. Yes, to find that you have to vector sum. Please understand that. Excellent. Yes, Vijay Kumar, I will definitely prefer H.C. Verma book for basic theory, basic problems, conceptual understanding, derivations and all important stuff. Over that, I would obviously prefer previous year's questions and the Tattva module which Vedantu gives. Alright, so once you have noted down all these things with me, and if you keep noting down things with me, then you don't have to wait for me so long. Alright, so I'm just erasing this. Based on this, no problem, Vijay Kumar, anytime. So guys, if you still have any doubts, remember after the class you can always message me on Instagram, Shreyas_Vedantu, or you can also post it in the comments. So either me or the channel managers will definitely help you and respond to you. Okay, now magnetic field due to a current carrying straight wire. Very important formulas coming up. Note it down. I'm going to give you some magical formulas also. Okay, the first formula. Due to a straight wire carrying current and you are at a distance r from it. So what is the magnetic field at that point? Now it depends whether the wire is infinitely long or is it finitely long. Let's say it is not infinite. That means there is a defined length. Then the first thing, guys, you should do is from the endpoints to that point where you want to find field, just draw imaginary lines. This is R and measure this angle as, let's say, alpha, and let's say this angle as beta. These are alpha and beta. These are the angles made by the perpendicular distance till the endpoints on both sides. Now the magnetic field is given by, okay, anybody knows what's the formula for a finite wire? Come on, how many of you know that formula? So guys, let's see, who writes it before me? Mu naught I by 4 pi r sine of alpha plus sine of beta. This is that formula which you should remember. Very, very important. Mu naught I by 4 pi r sine alpha plus sine beta. I is the current. Mu naught by 4 pi is 10 to the power minus 7. R is nothing but the distance. Now, Mohammed, I'll tell you where that formula is used. Pay attention, Mohammed. Very good, but I'll tell you where that formula is used. So, if you have infinite wire, infinitely long wire, then guys, think about it. Your point will be subtending almost like 90 degrees angle, almost like 90 degrees, tending towards 90 degrees angle at that point, both those ends. Think about it, this point and this point are there and here. If they are there and here, what is the angle alpha and beta? Think about it, it will almost tend towards 90. So guys, think about it, if sine 90 is 1, sine beta which is 90, so that will be also 1. 1 plus 1 is how much? 2. This 2 will cancel with this 4. So what will you get? You will get mu naught I by 2 pi r. So when will you use this formula, guys? Only for infinite wire. This is for finite wire. Be careful. So you should know this. Very important. Excelente, excelente. VK, Saurav, Fida, Selva, very good, Kirito. Excelente, excelente everyone. Very good. Alrighty, alrighty. I hope you have noted down all these important formulas. No problem, Princey, don't worry. Yes, very good, catching up. Very good, Khushbu, very good. For semi-infinite wire, Saurav, semi-infinite means, you know, you are here. So one of the angles will be 90 degrees and the other angle beta will be 0 degrees. So use it. So beta is 0, sine 0 is 0, sine 90 is 1. So it will be just this formula, mu naught I by 4 pi r. Alright, I hope this is clear. Very good, that's semi-infinite wire. Alrighty, let's get going to the next part. Next is due to a loop. Many important things coming up now. Lot of important things coming up. Direction has already been decided, discussed in the first part of today's session. In case you have missed it, do not forget to watch the replay. So, at the center, what is the magnetic field? Magnetic field at the center. So the magnetic field at the center, guys. This is obtained, all these formulas are obtained via integration. All those derivations are there in your NCERT or in HC Verma. So due to each element, you find the magnetic field and you add it up to get the net field. That's how these things are done. It comes out to be mu naught. Okay, so mu naught I by just 2 times. Okay, so the radius needs to be given. So let's say this radius is r. So it will be mu naught I by just 2r. And if there are more coils, more turns on it only, if there are more coils, then this I can be just multiplied by n if this is nothing but number of turns. If this is number of turns, very important. Okay, so magnetic field at the center. Okay, now next important formula coming up, very important formula. If you are here and let's say this distance is x, then at this point the magnetic field on that axis will be slightly different. In fact, because you are away, remember the field lines are going to diverge. It's going to be little bit less, it's going to be weaker. The magnetic field on the axial point anywhere will be very similar formula, mu naught I by 2, but instead of r you have r square plus x square whole raised to 3 by 2. Now remember, dimensionally always length is below. Look at that, length is below, guys. Now if you see dimensionally, this is length square, alright, and then cube and then square root. So square and square root will get cancelled dimensionally. Only cube will remain, correct? Only cube will remain dimensionally. So to nullify it and to only have length below, you need a square of length on the top. That's how I remember this formula, and that will be r square. That's it. It is not x square. Why is it not x square? That also I know, because if I put the value of x over or whatever over here 0, remember I should get back this formula. Just see this. If I put the value of x as 0, I should get back this formula, and just put x as 0, guys, you will get this formula. Remember, if this was not r square, if this was x square, then the entire term will become 0. No, the term will not become 0. Very, very important. I hope this is clear. Very important formula. This is for the actual point. Okay. So erasing this formula. Remember, if there are more coils, it will be multiplied by n. That's it. That's the only difference. Alrighty, alrighty. Okay. Don't worry, Vijay Kumar. You can always go back a little, because that's the advantage of YouTube. You can always go back a little and come back in case you have missed it. Don't worry. And anyways, all the sessions get recorded, so you can always replay back the sessions. Let's get back to some problems now. Okay. Remember, just some time back we solved this problem only for direction. Now let's talk about magnitude. So let's assume that the distance between them is d, and if I ask you what is the magnetic field's magnitude over there, we had just discussed that due to this wire, okay, this was I1 actually, due to this wire the magnetic field was inside, and due to that wire it was outside. So the net field, all right, was B2 minus B1. Why B2 minus B1? Because of this. Current I2 is higher. This is higher. So field due to current 2 is higher than B1. And what will be B2 and B1 respectively? Okay, these are infinitely long wires, guys. And point P is at a distance of d by 2. So just use the formula. Mu naught I by 2 pi distance is d by 2, but this current will be I2, and second time it will be mu naught I will be I1 divided by 2 pi r. R again will be nothing but, understand, d by 2. So just 2 gets cancelled, and you will have mu naught by pi d, and you will have bigger current minus smaller current. That is the net magnetic field. I hope this is clear. Alright, so they are carrying currents in the same direction, and the question is find the magnetic field at point P. Understand, this current produces magnetic field, this current produces magnetic field inside, even though the direction of currents are same, and this current produces magnetic field outside. That's why I have subtracted. It's not addition. Lot of people do the mistake of putting a plus here, looking at, oh sir, the currents are in the same direction, right? So it will add. No. Think about it. Use your right hand rule. No problem, Vijay Kumar. I hope this is clear. Yes, and it is not r square, it is just r. Be careful. No problem, Anjana. I'm always there till the end. In fact, not just till the JEE examinations, even after that, till your counseling, till you get your college seat. You guys are going to tell me which college you got into, which college, which branch you got into. Definitely you're going to do that. Isn't it right, minions? Tell me. Alright, let's get going to the next question. Very good question. The magnetic field at this point O is. The magnetic field at this point O is. Okay, come on guys, let's see how many of you do that. Meanwhile, let me just sip through. Hello Karthik Reddy, come on, join in. Start solving the question. All right. Okay, let's have a look. Let's have a look. A lot of you said B. A lot of you are saying B. Some of you said C as well. Yes, Fida, very good. You will be a doctor. I will be very happy. Yes, surely, Khushbu, I'll just check it out. but please post it on the recent videos, because if you post it on very old videos, it's very difficult to check. Post it on the recent ones. Okay, let's have a look. Well, guys, the correct answer is C. Okay, now you'll be like, sir, you never told us the formula for semicircle. Don't worry, I'll tell you. I have actually told you in a very different way, and you'll understand it. No problems. Now, because of this wire, all right, because of this straight wire, understand, you hold your thumb in that direction, you will see the fingers curl this way. The field at point O should be inside, guys. It should be inside, correct? The field at point O should be inside because of this current. Now, similarly think, because of this current, correct? The current goes like this and comes like that. Because of this current, the field should come outside towards you. Oh, best part, guys, these two just cancel out each other because they're equidistant. Come on, think about it. Because of this, it is inside, distances are. Because of this also, the distances are, the field is here. They will cancel each other. So we don't even have to worry about the straight wires at all. So who is contributing over here? Only the semicircle, guys. Now, what is the magnetic field due to a complete circle? It is mu naught I by 2r, correct? It is mu naught I by 2r. But a circle has two semicircles. Each one contributes half of it. Each one will contribute half of it. So, what is the magnetic field due to a semicircle, guys? It will be exactly mu naught I by 2r, half of this. So that's why the answer is mu naught I by 4r. I hope this is clear. Understood? Understood? Khushbu, this is the second lecture. The first lecture was over, I think 2 days back, but that was forces due to field. This is an independent chapter where you are just learning field due to current. So in a way, it's an independent chapter. All right. Okay, so let's get going to the next question. Let's see how many of you get this. The electric current in a circuit coil of 2 turns, okay, there is a coil of 2 turns, produces magnetic field, magnetic induction is same as magnetic field, of 0.2 Tesla at its center. The coil is again removed and again rewound into a coil of 4 turns. The magnetic field at the center of the coil is now how many Teslas? I would like to have at least 1 Tesla, yeah. 1 Tesla car. All right. Come on, Mohammed. All right. Kirito says D. Okay. Come on, everyone. Selva says D. All right. Mohammed says A. Kirito changed his mind to B. Saura says D. Oh, sure, Khushbu. Definitely, I'll check it out. So, radius will reduce. Yes. A lot of you are saying B. Some of you are saying D. All right, Anurag says D. Okay. So, let's see, guys, what should be the correct answer. Come on. Okay, so let me show you the correct answer. The correct answer is D. Well, so I'll tell you why, guys. See, earlier it had 2 loops, okay, and here there was some magnetic field. B was mu naught I but into 2, because there were n was equal to 2 loops, by 2 into r. This was the radius r. Now what you are doing is you are unwinding it and again winding it, but this time 4 rounds are made. If n is equal to 4, can you think the radius will be, understand, half of that, because the number of rounds are doubled. Earlier it was 2, now it is made 4. So if you double the number of turns, understand the circumference will reduce. So understand you have to have half the radius. I hope this is clear. Correct. So now the new magnetic field will be mu naught I, but this time it will be 4 by this time 2 times r by 2. Great. 2 cancels. Correct? 2 cancels. And you will have mu naught I 4 by R. Now think about it. Over here, this 2 and this 2 gets cancelled. So if this old B was how many Teslas? 0.2 Tesla. So naturally, the new B will be 0.2 multiplied by 4, which is nothing but 0.8 Tesla. That's it. That is the answer, because this much part, mu naught I by 4 R, is nothing but this one over here, which is 0.2. That's it. That's the answer. So a lot of people get confused and mark different answers. But if you solve it correctly, if you have patience and if you have concentration, you will not do silly mistakes. So that's how you need to do this problem. Let's get going. Correcto. Correcto. No problem, Khushbu. Even if you proceed in the comment section, no problem. Very good, Poke Tech. All right. I'm seeing you are a new user. Very good. Very good. Keep it up. Now this is a very good question. Very good question. There is a polygon. Yes, there is a polygon of n sides inscribed in a circle of radius b. That means imagine something like this. Imagine something like this. There is some polygon like this, and there is a circle which is like this. And the radius of that circle is b. That's what is given to you. Okay. So now the question is, if the current flowing through that is I, what is the magnetic field at the center of that loop when the polygon, luckily for us, is n is equal to 3. Now if you know how to solve it for n is equal to 3, you can solve it for any other polygon. N is equal to 4, 5, 6, doesn't matter. So first let's think about the circle. This is how the circle is going to be. It's going to have some radius. Okay. Now here is the catch. Look at that. Guys, this wire is a finite wire. This wire is a finite wire. This wire is a finite wire. Okay, first of all, let's get rid of that circle. I don't need it. Oops. Yeah, I don't need that circle. Okay. Now, think about it. Due to each wire, what will be the direction of field? Let's say, let's say the current is flowing this way, then if you hold the thumb this way, the field goes inside. Correct? Now, because of that wire, also the field will go inside. You can try it out. And when it comes like this, also it comes inside. That means it's very clear the net magnetic field will be 3 times the magnetic field due to each wire out there, which is basically a side. So magnetic field due to each side, whatever is being produced. Now how do we do that? Well, that's not difficult. Here is a logic. See guys, from here to here, that is distance b. Why? It's clearly mentioned in a circle of radius b. This is the center of the circle, this is the radius of the circle. Remember, I had just shown you a circle just some time back. So this is the radius of the circle. This is an equilateral triangle, correct? Now this is an equilateral triangle. How much will this angle and this angle be equal to? Obviously, both of them will be 30 degrees because total angle must be 60. 60, 60, 60. So this is angle bisector, so 30 and 30. I hope everybody has understood. Next, this is a distance from that wire till the point where you want to find the field. So I'll just mark this as perpendicular. And think about it. How much will be this distance? Okay, come on guys, this distance is not that difficult. This is hypotenuse. This D is opposite 30. So it should be B sine 30. That means it will be B divided by 2. Okay, I got that also. Now, last thing remaining is what is the length of this side? What is the length of that side? So before that, what will be this much? This will be B cos 30. So it will be B cos 30, which is nothing but B root 3 by 2. So if this is B root 3 by 2, what will be the length of the side, guys? So what will be the length of the side? It will be twice of that. So it will be B root 3. Okay. I don't know if I need it, but I just kept it in case I need it. I'm not sure if I'm going to need it, but I just kept it. Okay. I hope this is clear. Okay. So it's a regular polygon. Look at that. It's a regular polygon. So if it's a regular polygon, it has to be equilateral. Okay. Okay. Very good. Now, if this much is understood, Now think about it. What will be the magnetic field due to any one wire at this point? Recollect that formula I gave you. What was that formula? Mu naught I by 4 pi. Remember, that was mu naught I by 4 pi into sine alpha plus sine beta. What was alpha and beta? This and that angle. Now believe me, both these angles will be same. This is the perpendicular. From the endpoints, you join those lines, whatever this angle, how much will it be? 60 degrees, isn't it? 60 degrees and 60 degrees. Symmetrical, equilateral triangle. So sine 60 plus sine 60, guys, divided by, what is it? Divided by distance. What is that distance? Come on, guys, it is nothing but b by 2. I hope this is clear. So this will become 3 mu naught I, okay, and this 2 and this 4 gets cancelled, so you will have 2 pi b, okay. Sine 60 is root 3 by 2, but there will be 2 root 3 by 2's, so 2 into root 3 by 2, 2 2's cancel, and that's it. You should have 3 root 3 mu naught I, 2 2 have cancelled, root 3 has come there, divided by 2 pi b. Just check this out. That is the final answer. Yes, guys, please read the question. It's a regular polygon. That's why it's an equilateral triangle. Very good. Okay, I hope this is clear. Is this clear? What a nice question. This is a proper JEE advanced type of question, or a KVPY type of question. Okay, well, shall we go ahead? Everyone clear? Oh, yes, crystal clear. Very good. Excellent. Let's get going. So we are going to make the challenges, problems really challenging now. So now let's talk about forces due to the wires. Forces due to the wires. Now remember, I have told you that whenever magnetic field affects a current carrying wire, the force given by Lorentz force is I L cross B. I L cross B. Remember? Now a wire which carries current obviously produces magnetic field around it. Now what if that magnetic field affects another wire? This is what is going to happen. So imagine currents are flowing in the same direction. Just imagine currents are flowing in the same direction. So hold your thumb. Let's talk about this left side wire. The field due to that will be like this, correct? The field due to that will be like this. So on this wire, the field will be going inside the plane of the board. Come on. The field due to this wire will be going inside the plane of the board. Okay. So the field is going inside. The current is going this way. The current in this second wire is going this way. Now what happens, guys? The force due to magnetic field, I L cross B. Where is L? If the current is flowing here, length is also there. Length cross B. Length cross B. Where is it coming? This way. It's coming this way. That means this current's magnetic field pulls this wire towards itself, and the same way you can argue that this wire will also be pulled towards that wire because of this wire's magnetic field. So there will be a force of attraction. There will be a force of attraction. And if the currents were opposite, then there will be repulsion. So opposite is repulsion here, same is attraction. It's very opposite to your charges. In charges, same charges repel, but here same currents attract and opposite currents repel each other. So that is different here. That's how you remember it. That's how you remember it, guys. Okay. Now, what is the force between them can be found out very easily. Let's say the distance between them is D, example, and the currents are, let's say, I1 and I2. Okay. Now, the magnetic field due to one. So this is magnetic field due to I1 at I2. How much will it be? It will be mu naught I1 by 2 pi D. D is the distance, or that R over there. Now, the force on I2 due to B1 will be given by I, which is I2, L, which is the length of that wire, I don't know how much it is, cross B. Now B is this B, understand? And this is going to be 1, guys, because remember the angles are 90 degrees. We had just discussed this. The length is here, this B1 is inside, so length cross B, guys, will be 90 degrees. So sine 90 is 1. So that force on that wire 2 will be equal to I2 L, and this B1 is this value, which is mu naught I1 by 2 pi d. Rearrange it and bring this length down. F2 by L will be mu naught I1 I2 by 2 pi d. Now this is a formula which you should remember, guys. Force per unit length. This is force per unit length, and you should know this. Mu naught I1 I2 by 2 pi d. It will be attractive if they are in the same direction and repulsive if they are in the opposite direction between the two wires. Okay. Okay. I hope this is clear. All right. Aishwarya, marathon is a part of the Flash series only in a way. Flash is basically where we conduct sessions usually for 1 hour. In marathon, we conduct the sessions for 2 hours or more than 2 hours. Okay, I hope this is clear. You're noting it down. So let me grab my stuff out here, and I have got some nice banana chips. How many of you love banana chips? And these are from Kerala. Yes. One of my relatives went to Kerala and he got banana chips for me. So cool. Guys, have your break, have your food, and let me know what you guys are eating. Yes, you will be learning about permeability and permittivity very soon in the next week. Shalva, come on, there will be something in the kitchen. If nothing is there, at least eat sugar, man. These chips are so yum, yeah. What should I say? So yum. Chocolate, science players are having chocolate. Shreya, I think the 4 attempts are very good. It will improve your chances. You can boost your performance. That's very good. Aishwarya is having cucumbers. Kya baat hai? Jumna, hide and seek. I love hide and seek. Yeah. Salted pistas. Yeah, even that's my favorite. Anurag. Daimi, you can also make me jealous by telling me what you are eating. Well, VK, I usually take it from hot chips out here. Tofu, what is tofu, yeah? Oh, Selva, Bonvita powder was my favorite to until a long time, yeah. Shreya, I don't know, yeah, what will be the cutoff. It's going to be very dicey. It's too early to say and nobody can predict it. Oh, very good. Please tag me with your chocolates. Dinesh, having cup of tea. Which kind of tea? Normal tea or any masala tea? Wow, Fida having butter cookies. Wasim sir, Saqib, I think he's not well, most likely. Tofu is cheese. Acha. Tofu is paneer. My God, one person is saying cheese, one person is saying paneer. Decide kar lo. Acha. Oh, by the way, there is a special session coming for all of you on 1st January. And who is it going to be conducted by? Shreyas sir. Okay, so wait for it. 1st January, I'm going to conduct a very special session for all of you. And it is going to be a casual talk. And there is going to be a big surprise for all of you. A very nice thing. I'll tell you what it is. You will love it. You will love it. You will love it. Okay. Chalo, let's get going to the next part, guys. I hope you're all energized, refreshed. Let's get going. Here's your first question coming up on your screen. two long parallel current carrying conductors repel each other with a force F. If the currents in them are doubled and the distance between them are halved, then the force between them become how much? How many times? How many times? All right. Come on, think about it, guys. How many times do you think the force will become? All right. Yes, lot of energy. Yes, we need that energy, guys. Okay, some of you are saying C. Come on, what about others? Come on, everybody post it. It's okay, you can be wrong. Even if you're wrong, it's okay. Nobody's going to judge you here. All right, some of you are saying B, some of you are saying 4 times. Okay, B, that is C. Okay, very good. So guys, let me tell you, the correct answer is actually 8F. Now I'll be like, what the hell, why? Guys, the force between them, remember I just gave the formula, force per unit length is mu naught I1 I2 divided by D. Now guys, read the question carefully. Their currents are doubled. That means this is doubled, this is also doubled. The distance is halved. That means this 2 will also go on the top. 2 into 2 into 2. How much is 2 into 2 into 2? It is 8. So hence the answer is 8. Understood? Yes, correcto? No problem, Karthik. It's okay. Alright. Let's get going to the next question coming up on your screen. Wow, looks like a big question, but it's not so difficult. Let me assure you with that. There is a square which carries current. Oh, I think there is one thing missing though in these options, and that is A. So I think A is missing in all these options. So now think about it. This current carrying loop is at a distance A. How much is the force because of this wire on this wire? Net force. How much is the force because of this wire on this wire? And distances are given, currents are also given. What do you guys think? Is it difficult? Is it very difficult? Yeah? I don't know. You tell me. Let's see how many of you can get this. It's okay even if you get it wrong. Just post it, guys. Try it out. 0 says Saurav. Alright. Okay, I don't know. We'll figure it out. Kiruto says C. Okay. Now, okay, many of you are saying A, C, some of you also said D. Interesting. B, C, alright, D, alright. Now, lot of you might have thought this, correct me if I'm wrong. Sir, this is a loop, and you only told us yesterday that if it's a loop, then the net force is 0 due to a magnetic field. Yes, I told you. But when did I tell you? I told you when the field is uniform. When the field is uniform, only then the net force is 0. But is this field uniform? You only think for yourself. Obviously not. Why? Because at different distances, the field due to this wire I1 will be also different. Here it will be strong, here it will be weak. So you cannot apply that rule. Understood? So hence the answer most likely will not be 0 unless for some special purpose it has become suddenly 0. Okay, so it is not 0. Now how to solve this question? Very simple. See guys, first of all what you do is, because of this current, use your right hand rule, put your thumb in this way, your fingers will curl like this, so the magnetic field will be inside. So due to this wire, understand the magnetic field is inside B1. Now just think what will be the direction of forces on each part. Like for example, if the magnetic field is inside, for this wire on the top, guys, use IL cross B. That's the Lorentz force formula. L is here, B is there. L cross B. Like this. Take your right hand, use your 4 fingers, point it that way. That's in the direction of current. L cross B. The force comes inwards. Now yesterday I told you one trick. Once you have a loop and you know force on any one side, automatically other forces are also going to be inwards. If this was outward, then all other things will be outwards. You don't have to do this bhajan 4 times. Okay, so don't have to do this so many times. If you know only one direction, automatically others will be inside. If it is outside, then everything else will be outside. So don't do this bhajan. All right. Now think about it. This force, okay, if I call it F1, if I call this F2, if I call this F3, and if I call this F4, think about it. These two currents like this, their forces will cancel. So F1 cancels F3, but F2 and F4 won't cancel each other. Reason, understand F2 is closer and F4 is far away. So understand that the net force will be F2 minus F4, and F2 will be larger, it will be stronger. Understand, it will be stronger, and F4 will be weaker because the field over there will be weak. Very, very important. Very, very important. Yes, I will have marathon for other topics also. Don't worry, everything is coming. Just have patience. Okay. Now, here F2 will be, what will be F2? I, okay, current in that, which is I2, into length. How much is the length? A, okay, into B, okay. B due to this one, this wire. What is the magnetic field due to this wire over there? It will be mu naught I1 by mu naught I1 by 2 pi, correct? 2 pi distance. What is the distance? A. I hope this is clear. This was nothing but the magnetic field due to this wire at this point. F2 is done. Next, minus F4, force on this wire. IL cross B, current in that wire is I2, L is A, and B is mu naught I1, because field due to this current, and distance is, believe me, 2A. Look at that, this distance is 2A. That's it. And then you get the answer. So, oh, A is getting cancelled. I think I told you guys that A is there. So I think the options were correct. So A is going to get cancelled. That's a good thing. So mu naught I1, I2, okay, and you have pi over, oh, I think I missed the pi over there. All right, pi should be there. So you have pi and oh, and this was one more 2 was there, guys. Oh, I think I missed that one more 2. Yes, there is going to be 2 pi r, and that r itself is 2a. Yes, that one more 2 was there. One more 2 is there. So it will be 2 pi, and then I will have over here 1 by 1. Okay, a has got cancelled. That's the best part. A has got cancelled. And I will have 1 by 1 minus 1 by 2, which is again half. So it will become 1 by 4 then. 1 by 1 minus 1 by 2 is 1 by 2. 1 by 2 into 1 by 2 will become 1 by 4. So I will get this mu naught I1 I2 by 4 pi. That's the answer. I hope this is clear. I hope this is clear. Is this understood, everyone? How to solve this? Is this understood? Okay? So do not miss that 2 out there, because the distance will be twice. Very important. Yes, clearo? Very good. So very good problem. And by the way, the force will be repulsive because that force is bigger than this force. All right. Clear. Excellent. Excellent. Okay. Next question. Okay. Before that, let me also tell you. So a lot of questions coming up now. But before that, guys, for all the 12th and the dropper students who want to enroll in crash courses, let me tell you guys, these crash courses start every Monday. Okay, so you will not miss anything. There will be 120 sessions, 10 full syllabus and 10 part syllabus test series for your practice. And these 120 sessions will be basically as per the new pattern and also the tests, and also you will be taught, or you will be doing the revision of all the syllabus, JEE Mains. And there will be doubt solving from morning till night for all your doubts in the Vedantu app itself. And there will be some special sessions for tricks and tips to crack the JEE Mains 2021 examination. So all this will be available at a very affordable price of 10,000. But if you use the discount coupon SHCC, then you can get 20% straight off. You can first visit the link which is there in the description box below. Read everything carefully and do not forget to apply the coupon code, because you'll be getting straight away 2,000 rupees off. 8,000 rupees is nothing considering what we are giving you for the next few months till your JEE Mains examination. So guys, if you feel that you have not prepared well for the upcoming entrance examinations, go ahead and check out the crash course details. It is meant exactly for you who feel that their preparation is not so sufficient. Okay, now let's come to Ampere's law. Okay, so now Ampere's law is very important because it helps us avoid integration. If you remember guys, I told you about Gauss law in electrostatics, and what did Gauss law help us do? It helped us calculate field due to different geometries in a simpler manner. Same way, Ampere's law also helps us calculate magnetic field in a much similar fashion, and it helps us avoid integration in many places. Now, the irony is Ampere's law involves the symbol of integration, but like I said, the irony is it helps us avoid that integration. So there is a symbol, but it helps us avoid. So we'll see that. Hold on. Now, what do you need for an Ampere's law to be applied? First thing, you need 1 or 2 wires. Okay, doesn't matter. And you need an imaginary path, which is a closed path. That closed path is called as an Ampere's loop. What is it called? Ampere's loop. Like in Gauss's law, a closed surface was called as a Gaussian surface. So first thing you need over here is a closed path where you start and end at the same point. This is an imaginary path, remember that. It's called as Ampere's path or Ampere's loop. Now, like I've shown over here. Now, you start traveling along that path by small distances. What is that dl? That is the distance by which you move. What is B? Magnetic field. Due to whom? Due to all the wires. Yes, very important. This B is the magnetic field due to currents inside and out of the loop. Very, very important. So this is the resultant magnetic field due to the currents inside the loop, like I1, I2, and the currents which are outside the loop. Now, when you take the dot product of magnetic field with that distance and slowly do the same thing for every point on that loop, every point dl dot b everywhere, and you integrate it and come back to the same point. Now when you come back to the same point, symbolically it is represented like this. This stands for basically cyclic integral. Okay, so this is called a cyclic integral or a loop integral. Then the value of this, surprisingly, always comes out to be whatever currents are inside, enclosed inside, okay, into, so instead of divided by, here you have multiplied by. Understand? So mu naught into I enclosed. That is the formula. Now this is what you are supposed to remember. This is called as Ampere's loop law. This current over here is whatever is there inside that loop. Remember, inside that loop. This current will not even matter. Now, very important, what should be the signs of I1 and I2? Because how do I take the signs? So here is the convention which we are going to follow. If you are going to go across the loop like this, which kind of direction is this? If you are going like this, this is anti-clockwise. Okay, so curl your fingers then anti-clockwise. Your thumb will come towards you. Your thumb will come towards you. Any current which is towards you now will be positive, and any current opposite of that will be negative. That's why I1 will be positive, I2 will be negative. So in this case, the enclosed current will be I1 minus I2. Please don't add these currents. Just don't add them. they have signs. So the one which is positive is in the direction of your thumb. And how do you point your thumb? Curl your fingers in the direction of the path which you have traveled. That's it. I hope this is clear. Yes. So the outside current won't matter. I3 won't even come in the picture. This is inside the loop. Whichever currents are there, only they will matter. But remember one thing, this B is because of inside as well as outside. Okay? Chalo, let's solve some questions based on this. I hope you have written it down. Okay. Now, this is a very good question. Very good question. Let's do this. I want you to see how Ampere's law is applied. This is a wire carrying current. Usually, we used to find field due to a wire outside that wire, correct? Field due to a wire outside, which was mu naught I by 2 pi r. But now, that wire itself will have some thickness, correct? So this is that enlarged version of that. That wire has some thickness, radius, and I want to find if there is any field within that wire itself. Is there any field within that wire itself? So let's do this problem. First thing, let's mark the radius of that wire as r, and that radius or that distance at which I want to find the field as small r. So that blue thing over there is the distance from the center where I want to find the field inside that solid conductor. Now you'll be like, sir, where is the current? Okay, I'll tell you where the current is. So the current is going like this. The current is going this way and the total current is I. Now, I want to find the field at any point over here. I know the field will be in concentric circles. Okay, the field will be in concentric circles. So I'm just going to put over here, okay, in case you're not able to see it. Okay, so like this will be B, guys. This will be B. Now, the first step you should do is choose an Amperian loop. Choose an Amperian loop and show the fields approximately. Okay, if you know the direction. Now, I have already shown the field. The field will be like this. How did I decide that? Guys, if currents are like this, your fingers will curl this way. So the magnetic field lines will be like this, circular, along that blue dotted line. Now, I will choose my Amperian loop to be this one. So this is my Amperian loop, which I have chosen, and travel across that loop by small distances. So let's travel across that by small distances like dl. So dl, I'll keep on traveling. Now apply Ampere's loop law and let's see what happens. So what is Ampere's loop law? Cyclic integral B vector dot dl vector will be mu naught into I enclosed. Now very important, guys. What is B dot dl at any given point on that blue circle, that dotted circle? Oh, why have we not considered surface? Because Ampere's law is not applied for a surface. Ampere's law is applied for a path, for a loop. That's the big difference. Understand that. Okay? Now think about it. At any point, B vector and dl vector are in the same direction, guys. Can you see that? So what will be the dot product? The dot product will be B dl cos 0 degrees. Any point. No matter, even if you are here, B and dl will be in the same direction. That's it. Now, this is equal to mu naught. Current enclosed. Now, when I talk about enclosed current, beware. I am talking about enclosed current in this region. Yes, in this region, guys. Now, it will not be I. Be careful. Yes, it will not be I. Now, why won't it be I? Because that current was flowing through the entire conductor. Only through this part, a small part of current I will be flowing through it. So, what will be the enclosed current? Let's think about it. First, what will be the current density? What will be the current density? First, think about it. Current per unit area. If I take any area on this, how much current is flowing per unit area, guys? Think about it. It will be nothing but I divided by pi capital R square. That's current per unit area, whole area. So how much current will flow through this area? That density multiplied by area of that shaded part. So it will be nothing but I divided by pi R square into just pi small r square. Understand, pi small r square is the area of this part over here. You can see that. Now, if you have understood it till here, think about it, guys. Think about it. Think about it. B is constant everywhere, magnitude wise, because you are at the same distance, small r. So B will just come outside the integral because at the same distance on that dotted line, it's constant. So it will be just dl. What is cos 0? It is 1. And what will you get here? Mu naught I. This will become small r square by capital R square, correct? Now, what is this? Integration of all the lengths throughout this circle. The small circle that you see, integration of all the lengths. That is the circumference, guys, nothing else. So it will be 2 pi small r, I hope you get it, is equal to mu naught I r square by capital R square. Now what will happen? This small r will cancel with this r. So what will you be left with? You will be just left with B is equal to mu naught by 2 pi. Mu naught by 2 pi. Check this out. I is there. R is also there. But the only thing is you have r square below. Dimensionally, you still have one term of length below, because one length here will cancel, only one length will remain. So this is our final answer which we wanted. That's it. So there is magnetic field even inside the current carrying wire. But when R is 0, exactly at the center, it is 0. As you go away, it increases because here R is on the top. That's the strange part. When you're outside, this small r is below. When you're inside, this small r is on the top. So it increases from here till here, and then when you go outside, it decreases. I hope this is clear. I hope this is clear. Yes, the current density of the shaded part is also the same. In fact, the current density is same. That's why I could do that. What is the current in this part? It will be density into area of that smaller part. So current in this area will be density, which is same everywhere, into area of that part. I hope that is clear, Kirito. Oh, is everybody facing, how many of you are facing network issues? Is it? Oh, I'm not sure. I'm not sure why there is some network problem. Maybe from my end, because I'm at home, guys. And the studio, I'm not sure. I'm just checking if there is any light blinking out there. No. Okay, so acha. Okay, just manage, guys. Just few more things left. Okay, just don't worry, don't give up so easily, because recorded is not fun, and you can always you can just probably go back a little bit. If it's live is not working, you can probably play it in some 10-second delay mode or something like that, so it should be fine. All right, great. Let's get going to the next question. And solenoid, same thing is done for the solenoid, and you can find the field inside the solenoid. Now the field inside the solenoid, okay, again via taking an Ampere loop like this. Remember these formulas, all comes via Ampere's loop law. Mu naught Ni. Now be careful, guys. This N is number of turns per unit length. Guys, you know what? People get confused. So here is what I do. I will use capital N symbol for total turns, small n symbol for turns per unit length. So if this solenoid has 100 turns in 1 meter, then this small n will be 100 per meter. Understand? This is per meter. I is the current. Very important formula. Now I'll give you a special formula. Guys, you are in Shreyas sir's class. I won't give you normal formulas. I'll give you special formulas. Now what are these special formulas? Yes, these kind of questions do come in the examination. These kind of questions do come in the examination. Now I'll tell you what it is. Short solenoid. Not many people know this formula. Some of you might know it. Guys, short solenoid, when it is there, then the field is not constant. Remember that mu naught Ni formula is valid for long solenoids, infinitely long or very long. But when the solenoid is short, then the formula is very different. So, if you are somewhere here inside and you draw two lines like this, yes, two lines like this, and drop a perpendicular here, and now say that this angle is alpha and say that this angle is beta. So you are somewhere here randomly inside. Alpha and beta are variables. So if you go more inside, alpha beta will change. If you come outside, alpha beta will again change. Then the magnetic field, yes, the magnetic field at any point is given by mu naught Ni. Okay, so mu naught Ni. Here you have sine alpha plus sine beta and the whole thing divided by 2. Don't believe me? It's okay. I'll make you believe. How? Imagine this was infinitely long. Just imagine, okay? If it is infinitely long, what will happen to the values of alpha and beta, guys? Alpha will be 90, beta will also be 90. Sine 90 is 1, sine 90 is 1, 1 plus 1 is 2, 2 divided by 2 is 1. So what will you get? Mu naught Ni, isn't it? So we'll get back the original formula. So this works for short solenoid, long solenoid, every solenoid. Alright? Very good, very good, very good. Excellent, guys. I hope this is clear. Yes, very similar to the straight wire. Yes, correct, correct, correct. Now, let's go to the next formula, guys. Let's go to the next formula. Very important formula again. Not many people discuss this. A sheet carrying current. Yes, a sheet carrying current. So imagine this is a sheet in XY plane and currents are flowing like this. Imagine lots of wires in one plane, like these fingers represent wire. Wire 1, wire 2, wire 3, wire 4. Many currents are flowing in this direction. Now, imagine guys, if there was a wire coming towards you like this, the magnetic field because of that wire is this way, right? The magnetic field due to one wire is this way. Now, if there are many wires like this, currents coming towards you. Currents are coming, example, towards you. Okay? Then, what happens is, you can visualize it, it's not that difficult. The magnetic field produced because of these currents is going to be like this. Because look at that, on the top it's towards your left and bottom it's towards your right. So it is like this over here. This is B over here, and best part guys, this B is uniform. Yes, no matter how far you go, assuming this is a very large sheet, this is a very large sheet, then it is a uniform field. Very, very important for you guys to know. How much is the value? Okay, the value is mu naught, okay, lambda by 2. I'll be like, sir, I always forget this formula, it's very confusing, can you please tell me a trick? Yes, I'll tell you a trick. Guys, due to a charged sheet, do you remember the electric field formula? The electric field was, yaad karo, sigma by 2 epsilon naught. It was sigma by 2 epsilon naught. Now I'll tell you one thing. Magnetism, if it is like this, electricity is like this. You're always opposite to each other. Similarities are there, but you will find always something is opposite. Like in electrostatics, Gauss law had closed area. In magnetism, Ampere's law has closed loop. In electrostatics, you will see 1 upon 4 pi epsilon naught. Epsilon naught is below. In magnetism, you will see mu naught by 4 pi. Mu naught is on the top. So it's, if one is here, the other one is here, like this. So now, think about it. This was a charge sheet, right? What is sigma? Charge per unit area. In magnetism, what do you have? Charge, so it's not charge, it's current per unit length. So you might be wondering what this lambda is. Hold on guys, I'm telling you everything, I'm not going anywhere. This lambda is current per unit length. Current per unit length means what? Say for example, you choose this much length. In that much length, how much current is flowing? Example, 10 amperes is flowing per 1 meter. So lambda is 10 ampere per meter. How much current flows in 1 meter? That's it. So instead of areal density, you have linear current density. That's the difference. And where is epsilon? Below. So in magnetism, where will be mu naught? It will be on the top. Now will you forget it? Now will you forget it? You'll never forget it. You'll never forget it. Very similar formulas. Very similar formulas. Did you guys enjoy this trick? And guys, if you're enjoying all these tricks, enjoying all these sessions, guys, do not forget to hit that like button. If you have forgotten to hit the like button, go ahead, hit that like button if you have not done it yet. All right. Very good. Very good. So remember this formula, very important. Magnetic field is uniform. So it comes again using Ampere's loop law. If you take Ampere's loop law, you will get this formula. The derivation is there in the books. Last thing out here, toroid. Now again for toroid, if you take an Amperian loop, you can find the magnetic field. Okay. So guys, if you have a toroid of average radius r, and n is total turns. Please understand, this is the radius of the toroid. There will be one more radius if you realize it. This radius over here, the radius of that cross section. So this r is basically radius of circular section. That is not what I am interested in. In fact, that will not be there in the formula. You will see the magnetic field inside the solenoid will be, toroid will be mu naught n by 2 pi r into I. Now I'll be like, sir, this formula is also difficult. Please tell me some trick. Don't worry, I'll tell you a trick. Guys, do you remember a solenoid is straight? And how do you form a toroid? Just bend that solenoid and it forms into a toroid, correct? Didn't I tell you this? So taking a solenoid, bend it, it becomes a toroid. Now what was the formula for magnetic field for a solenoid? It was mu naught n I. But what was this small n? It was turns per unit length of the solenoid. Number of turns per length of the solenoid. Now when you bend it, toroid is nothing but a solenoid, guys. So what will be the field? Mu naught Ni. So what is the turns? N. What is the length? Circumference. Look at the length of the toroid. It's circumference. Don't you see the similarity? It's the same formula. Yes. So the magnetic field outside, anywhere, be it at the center, outside, will be 0. So magnetic field outside the toroid will always be 0. Just like outside the solenoid, it's negligible or 0. Okay? Clear? Everyone? Understood the tricks? Understood the formula? Shall we go ahead to the last set of problems? Excellente, guys. Excellente. Okay. Let's get going. Very good. So use Ampere's loop law. You can derive this very easily. It's there in many of your books. Let's see how many of you can do this. There is a solenoid, a long one, and the current is as shown. Find the magnetic field at the center and at the end, the ratio of it. Find the ratio of the magnetic field at the end and at the center of the solenoid, which is on the axis of the solenoid. Come on, let's see how many of you can do this. Very good, Tushar. Very good, everyone. Chalo, let's do this. Okay, Tushar says 0.5. All right. I don't know. Let's find it out. So guys, the logic is here when I talk about the magnetic field, okay, this magnetic field will be given by, think about it, draw those lines. One line will be here, another line will be here. What will be the angle? That angle will be approximately 90 degrees, correct? It will be approximately 90 degrees. So it will be, because it's a long solenoid, read it carefully. So when you are at the end, the other angle alpha will be 0. Understand? So it will become mu naught n I by 2 sine 0 plus sine 90 degrees. That's it. Sine 90 is 1, sine 0 is 0. So 0 plus 1, 1. 1 by 2 is 1 by 2. So it will become mu naught n I by 2. That's it. Now think about it. When you are at the center, of that long solenoid, guys, what will be the magnetic field over there? What will be the magnetic field over there? Both alpha and beta will be 90, guys. So this B obviously will be just mu naught n I by 2 sine 90 plus sine 90. How much will it be? It will be just mu naught n I. Because 1 plus 1 is 2, 2 cancels, mu naught n I. I think I found the ratio what I needed. So that ratio will be near the end by center. So end divided by center will be how much? End is half, center is 1, so obviously it will be half. That's it. Very good, very good. Oh my god, VK channel, what is wrong? Be careful, man, be careful. I hope now it is fine, and please take care. Please take care, please take care. Okay, stay safe, guys. Be careful, be careful. Very, very important to stay healthy, stay fit, and not have any unnecessary drama and trouble in your life. Okay, so that will unnecessarily affect your studies. Okay, so get well soon. Okay, so let's get going to the next question. Okay, very good question. Last few questions, guys, coming up on your screen. I hope your Josh has not died off. I hope you are still high up in energy. Okay, come on, let's do this. Very good problem for JEE Advanced KVPY. Come on, let's do this. Now, this wire on the left side is, let's say, carrying current like this. Current density, linear density is lambda. The other current is having linear density 2 lambda, and it is going down like this over here. Okay, this is 2 times of lambda. Now if you look at it from the side view, this is what it looks like. Now this looks to me like a Gauss law problem, very similar. Let's do this. So in this plate or sheet, the currents are going like this. This sheet is like this, understand? This sheet is like this. Currents are going like this. Density is 2 lambda, and in this sheet the current is going like this, lambda. Now think about it. Use your right hand. If the current in this sheet is going up like this, because of that the magnetic field will be as shown by the curled fingers. So on this side the magnetic field will be towards you, and anywhere on that side the magnetic field will be away from you. Think about it. Put your thumb there. Field lines will go inside like that because of this sheet. Is that okay? How much will be the value of this field? Well, it will be mu naught lambda by 2. Correct? That's the formula, guys. Each field, uniform field, sheet ka formula, mu naught lambda by 2. Okay, clear. Now think about this sheet, and because of this sheet, what will be the direction first? Currents are going down. Fingers will curl this way. Fingers will curl this way. So when you are on this side, it will come towards you. So I'll show a dot. And when you are here, it will go inside. So cross and cross. And what will be the value of these green magnetic fields? It will be mu naught 2 lambda by 2, because that's 2 lambda. 2 gets cancelled. It will become mu naught lambda. That's it. Now you just have to find the magnetic field in these 3 regions, guys. This is region 1, okay, this is region 2, and this is region number 3. 1, 2, 3. So let's do this. B1. Think about it. Will these fields add or will they subtract? Will this field add or subtract? Obviously they are going to subtract. One is coming here, one is going there. But which one is more, guys? Think about it. Which one is more? Which one is more? Is this one, green one more or red one more? Obviously green one is mu naught lambda, red one is mu naught lambda by 2. So it will be more inside. So I think it should be, just look at it, it will be mu naught lambda minus mu naught lambda by 2. So hence guys, the answer will be mu naught lambda by 2, but that will be inside. So I'll put a cross there. Next, B2. What will be B2? Both are in the same direction, so they will obviously add. So it will be mu naught lambda plus mu naught lambda by 2, which is nothing but 3 mu naught lambda by 2. And where will it be? It will be inside. Last thing, B3. Magnetic field in this region. This is coming out, that is coming in. So bigger minus smaller. So think about it guys. It will be mu naught lambda, correct? Minus mu naught lambda by 2. So hence it will become more towards outside. So mu naught lambda by 2, but that is outward. That's it, we have found out this answer. Isn't it simple when you solve it step by step and if you know the formulas and concepts very clearly? I've just gone step by step. So in this region, both these sheets give magnetic fields. In this region also both of them, in that region also both of them. Just superimpose, combine all their effects. Alrighty, very good. Clear, everyone? Maza aa gaya? Fun? Alright. Do not forget to smash that like button guys in case you are not done it. And if you are a new user, do not forget to hit the subscribe button. Alright, let's see a question on toroid. Oh my god, Khushbu, I hope the light comes back very soon. But glad that at least the internet on your mobile or iPad or whatever is working. So there is a toroid, inner radius, outer radius. 3500 turns are given. Current in the wire is 11 amperes. What is the magnetic field inside the toroid? So guys, first understand what is given over here. What is given over here? See, this is our toroid. Okay, so these are the coils like this. And what they have given over here is that this radius is 25. Okay, and the other radius is 26. So guys, think about it. What is the average radius? The average radius will be half, just take 25 plus 26 by 2, which will be 25.5 centimeters, which is 25.5 into 10 to the power minus 2 meters. Now just apply the formula. What will be the magnetic field inside? What will be the magnetic field inside? Mu naught N by 2 pi R into I. This is the formula. Let's do this. I'll write it as mu naught by 4 pi multiplied by 2 deliberately into N, okay, divided by R multiplied by I. Now just substitute the values. What is mu naught by 4 pi? 10 to the power minus 7. 2 is as it is. N is given 3500 divided by R. What is R? 25.5. 25.5 into 10 to the power minus 2. Lastly, current. How much is the current? 11 amperes. So into 11. I hope I have taken into account all the terms. Now solve this. This value approximately should come out close to, just check if it is coming 3 or something. Just check how much is it coming. Yes, it should come out almost as 3. Almost 3 into 10 to the power minus 2 Tesla. That's the answer. Just check it out. Very good, very good, very good. Very good, Ankit. Keep making notes. Excellent. No, it's not C. Be careful, guys. It's not C. It's D. I think you guys have made some mistake. See where you made the mistake. See where you made the mistake. That current is also there. I don't know. I think you have made some mistake, guys. Please check it out. Okay. No problem, Khushbu. Watch the replay and then you can make notes. Okay. Don't worry. At least pay attention to in the class. Okay. Glad. Okay. So that's the correct answer. All right, guys. So this is your homework question for today. This is your homework question for today. I know some of you have posted the answers last lecture. I'll post the stars next time, guys, whosoever the stars are for this session and the previous session. Yes, I'm going to post all the stars who are going to post the answers in the comment box. And if you have some doubts, please post the doubts in the comment section itself. I'll be trying and responding to all these doubts. So this is your first homework question. This is your second homework question, 2 loops. So check it out. And this is your third homework question, 3 homeworks. All right, I hope you guys are going to do it. And where am I going to post all the answers? I'm going to post it on the official Telegram group of VEnthused. Go ahead, join it. The link is in the description box below. Do not forget to join that because all the updates are going to come over there. And guys, do not forget to join this crash course. In case you are a dropper or a 12th standard student, it's once in a lifetime thing. You're not going to write the JEE exam many times. So please understand, utilize this time. If you feel that for some reason you have not done well previously, now is the time to join the crash course. Go ahead, check it out and use the coupon code SHCC. You'll get the course instead of 10,000, you'll get it for 8,000 only. Okay. And guys, if you're new to this channel, you know what to do. Go hit the subscribe button. You know how much it is going to cost? Nothing. And if you're already subscribed, you know what to do. Well, go hit the like button, guys. You know how much it's going to cost. Again, it's going to cost you nothing, guys. All right. Saurav, maybe you can try it again. Maybe you'll get it. Yes. Take care, guys. And I hope you will keep coming. And if you still want to get in touch with me, you can get in touch with me on Instagram, Shreyas_Vedantu. All right. Good night. Sweet dreams. I'll be seeing you guys on Monday. Monday, 7 o'clock. Simple harmonic motion in detail. Simple harmonic motion, 7 o'clock. See you guys. Have a great weekend. Happy weekend. Enjoy your Sunday. Take care. Bye-bye. Love you all. Bye-bye, minions.